Hello everyone, my name is Joel Johnson and today I will present my project on predicting wine quality using aggregation models. This project involved data preparation, transformation, model fitting and final prediction. This project aims to model and predict red wine quality based on its physiochemical properties. The red wine.txt dataset used contained 1,599 red wine samples collected from Portugal. The quality score, denoted as Y, is based on sensory evaluations, with ratings ranging between 0 and 10. Five key input variables labeled X1 to X5 represents chemical characteristics such as acidity, sulfur dioxide levels, pH, and alcohol content. The dataset includes five key input variables and one output variable. X1 represents citric acid, X2 is chloride, X3 is total sulfur dioxide, X4 is pH, and X5 is alcohol. The output variable Y indicates wine quality scored between 0 and 10. These variables are selected based on their chemical relevance to wine taste, preservation, and overall balance. .text dataset was imported and converted into a matrix format in R. A random subset of 460 samples were selected using a set seed based on student ID, ensuring reproducibility. We explored the initial data distributions using scatter plots and histogram. The main objective was to understand the relationship between chemical properties and wine qualities before starting the modeling process. Here we observe the scatter plots between chemical variables and wine quality. For chlorides versus quality, a weak negative trend is noted, where higher chloride levels are associated with slightly lower quality scores. For pH versus quality, there is no clear correlation and the data points are widely scattered. For total sulfur dioxide versus quality, a slight negative relationship is visible, suggesting that sulfur dioxide levels may slightly reduce with reduced wine quality. The scatter plots show two positive trends. Higher alcohol content is clearly linked to higher wine quality. Citric acid also shows a slight positive trend with moderate levels associated with better quality wines. The original distribution of citric acid was highly right skewed, with values clustered near zero. A power transformation with P equals 0.5 was applied to reduce the skewness. After min-max normalization, the distribution became more balanced and symmetric, making it more suitable for aggregation modeling. The original chlorides distribution was extremely right skewed. A power transformation with P equals 0.25 was used to reduce skewness. After min-max normalization, the data became more spread out and better suited for modeling. The total sulfur dioxide distribution was highly right skewed. A log 1p transformation was applied to compress large values and reduce skewness. After min-max normalization, the distribution became more symmetric and balanced for modeling. Alcohol distribution was moderately right skewed, with lower values being more common. We applied a power transformation with P equals 0.5 to reduce skewness, followed by min-max normalization. After transformation, the data became more evenly distributed, making it better for modeling. Distribution was already fairly normal with no extreme skewness. However, the scatter plot showed a very weak correlation between pH and wine quality. Therefore, pH was excluded from final model. We selected citric acid, chlorides, total sulfur dioxide, and alcohol as the fine input variable. pH distribution was fairly normal but showed very weak correlation with wine quality. Hence, pH was excluded. Uh, the final input variables selected were citric acid, chlorides, total sulfur dioxide, and alcohol. Formed four variables: citric acid, chlorides, total sulfur dioxide, and alcohol. Power transformation were applied for citric acid, alcohol, and chlorides. Log 1p transformation was used for total sulfur dioxide. All variables were then normalized using min-max scaling, and quality was standardized using Z-score normalization. We evaluated for aggregation model using the transform data, weighted arithmetic mean, weighted power mean, and ordered weighted average. We compared models using RMSE, error, and correlations. Quadratic means achieved the best results with the lowest RMSE and highest correlations, and was selected as the final model. In the final model, alcohol and citric acid had strongest influence on wine quality. Chlorides had no impact, and total sulfur dioxide contributed slightly. We introduced new input values for citric acid, chloride, sulfur dioxide, and alcohol. The same transformations used during model training were applied to these inputs, including power transformations and min-max scaling. This ensures that the new data remains consistent and compatible with the model's training structure, enabling accurate predictions. The prediction was made using the transformed input data and our best selected model, the quadratic mean with p equal to 2. The model's output was initially on the transformed scale. To interpret the result properly, we applied the inverse of z-score transformation and rounded it to the nearest integer. The final predicted wine quality score is 6. To conclude, we successfully cleaned, normalized, and reduced skewness in the dataset. Quadratic mean was selected for its best error and correlation results. Alcohol and citric acid were key predictors of wine quality. The model showed strong predictive ability, highlighting the values of thoughtful data preparation and model fitting.